Okay. Today, two topics. In the first topic, I present formulas to compute determinants. And the second topic, I present the relations between determinants and row operations. First, about exam 2. Exam 2 is on next Thursday. The time is 11 to 12:15. The location is classroom building, the room 105, the same room as in exam 1. Exam 2 covers sections 1.7, 2.1, 2.2, and 2.3, 4 sections this time. How to prepare for the exam? My suggestion is review the homework assignments and pick some examples in the book to read. And also try some problems in the exercise sections in the book. You can have a formula sheet to the exam. The formula sheet, the size is A4 size. You can write any things you want on the formula sheet, on the both sides of the formula sheet. And also you can have a basic basic calculator. Okay, basic means your calculator cannot compute, say, a matrix times a matrix, right? Just a basic, okay. Low function for matrix operations. Yeah. This is about exam 1. About exam 2. Now, return to these two topics. Take a review first about what we learned in the last class. Take a review, okay? A determinant, it is a number. This number determines whether a matrix has an inverse. When determinant, this number, non-zero, then matrix is invertible. If this number is 0, matrix is not invertible. Review 1. Review 2. Some notations. Remember these notations. First, the notation for a determinant is this, and also this. The two vertical line here doesn't mean absolute value, but mean determinant. Second notation, Aij. This notation is the submatrix of matrix A. How to get this submatrix? Delete row I and column J from the matrix A. Then we have capital Aij. Yeah. The third notation is let Cij. Cij is a number, okay, not a matrix. This number is -1, and the power is I plus j times determinant of capital Aij. Determinant is a number, so this is a number. And we call this number, give a name, call this number the Ij. cofactor. The ij cofactor. Okay, yeah, this number we give a name, ij cofactor. Reveal A, B, then C. In the last class, we learned one formula to compute a determinant. The formula is okay. Case one. If matrix A is 1 by 1, say the matrix has only one entry. Say the entry is alpha. Then determinant of a 1 by 1 matrix is just the entry alpha. Second case, for a matrix of any other size, the formula is determinant of A is equal to, look at the first row of the matrix A. The first row, first entry is A11. Then times C11. C11 is from here. Cij. This is a formula for Cij. So C11, I is 1, J is 1. Then plus the second entry on the first row is A12. Then times C12 plus the third entry is A13. Then times C13 and so on. The last entry on the first row is A1. And I assume the matrix is n by n, a square matrix. Yeah, determinant is computable only for square matrix. A1n times C1n. Yeah, this is the formula to compute the determinant of a matrix A. Yeah, this is our review 1, 2, 3. Then review number 4. A D. For a 2 by 2 determinant, A11, A12, A21, A22 determinant. Then determinant I use vertical lines. Yeah, vertical lines. Don't use square brackets. If we use square brackets, that is a matrix. Now determinant use vertical line, 2 vertical line. Yeah, this means determinant. The formula is a 2 by 2 determinant. The formula is the product of the two main diagonal entries, A11, A22, then minus the product of the two anti-diagonal entries, A12 times A21. Yeah, this is the formula to compute a 2 by 2 determinant. This is a review about what we learned in the last class. Now, examples. Let me show you one more example about this formula. One more example. Example 1. Okay. Compute the following 3 by 3 determinant. 6, 0, 5, 1, 7, -5, 8, 3, 8. Determinant. Now I use vertical lines on the both sides. Yeah. Vertical lines is determinant. Square brackets, matrix. Okay. Okay. Now compute this 3 by 3 determinant. Solution. A formula is here. Yeah. Formula is here. Formula is here. Okay. Expand the determinant across the first row. By formula, this determinant is equal to A11 C11 plus A12 C12 A13 C13. Okay, now A11 is 6. C11 A12 0. C12 A13 5. C13. Okay. So this is a 6 C11. The second term is 0, right? 0 times C12. C12 is a number. It's a number. So 0. So plus 5. 5 C13. Okay. Okay, now here. It's equal to what is C13? C11. No, C11 is here. It is 6 times -1. 1 plus 1. Determinant of capital A11. Capital A11 is a matrix. Then plus number 5 times C13 by formula, by this notation here. By formula, C13 is -1, 1 plus 3. Determinant A13. Now simplify. -1, the power 1 plus 1. 1 plus 1 is 2. So -1 squared positive 1. So this is a 6 determinant A11. Then -1 to 1 plus 3. 1 plus 3 is 4. So -1 to the 4th, positive 1. Okay, now next, let me determine this determinant. A11 is the matrix obtained from the original matrix by deleting row 1, column 1. So this determinant is a delete row 1, column 1. Then only this part remains, right? So this is a 7, -5, 3, 8 determinant. Then plus 5 times capital A13. Capital A13 is the matrix obtained by delete row 1, column 3. Delete row 1, column 3. So this part remains. So this is a 1, 7, 8, number 3 determinant. Yeah, determinant. Yeah. So this is a okay. Now we need to compute these two 2 by 2 determinants. Formula is here. Formula is here. So this is 6 times the product of the main diagonal entries, 7 times 8, minus product of anti-diagonal entries, 3 times -5. Then plus 5, 2 by 2 determinant, 1 times 3, minus 8 times 7. Then calculator, the number is 161. So this 3x3 determinant is a non-negative number. Therefore, the matrix has invertible. Determinant non-negative. The matrix is invertible. So done. Okay, now we have one formula to compute a determinant, but this formula is not the only formula to compute a determinant. There are other formulas. We call this formula expand the determinant across the first row of matrix A. Yeah, we call this formula expansion across the first row. It turns out that you can expand a determinant across any row or down any column. Okay, so more formulas here. Yeah. Other formulas. Other formulas. Okay. A. We can expansion across any row. Say the ith row. The formula is this. Okay. Determinant of A is equal to row I. The first entry is row I. The first entry is AI1. Then times CI1 plus second entry AI2. Then times CI2 plus so on. Okay. Then AIN, the last entry, times CIN. Yeah. This formula is called expansion across row I. Or you can expand a determinant down any column. Expansion down any column, say column J, the J column. Determinant. The J column J. The first entry is A1J. Then times C1J plus second entry on the column on column J is A2J. Then times C2J plus A, the last entry is ANJ times CNJ. Yeah, these formulas are easy to remember. Okay. All these formulas will give us the same answer. Okay. So let me pick this determinant to illustrate the new formulas. Now this time, let me compute this determinant, say down column 3, Okay, example 2. Example number 2. Example number 2. Use cofactor. Yeah, cofactor Cij, capital C, cofactor. use cofactor expansion. Tóm the column to compute the determinant in example 1. 6, 0, 5, 1, 7. Yeah, to compute this determinant. Okay. Now the solution is okay. Dump the third column. Okay, solution. The determinant by formula, I expand it down the third column. The formula is 1 3, C1 3, A2 3, C2 3, A3 3, C3 3. Now A1 3, 5, A2 3, -5, so -5, 2 3. A3 3, number 8. Okay, now capital C1 3 formula is here. Yeah, formula here. It is a 5, -1, I plus j, so 1 plus 3. Determinant A1 3. Capital A1 3 is a matrix. -5, C2 3 is this number. Determinant capital A 2 3 plus 8. C3 3, -1, 3 plus 3. Determinant capital A 3 3. Okay. Now, -1 to the 4th, +1. -1 to 2 plus 3, 2 plus 3, 5. So -1 to the 5th, -1, but there is a negative in the front, so positive. Negative to 3 plus 3, negative to the 6, +1, so plus 8, A3 3, A3 3. Okay, now 5. Capital 1 3 is the matrix obtained by delete row 1 and column 3. So what remains is 1 7 8 3 determinant plus 5 capital A2 3. Delete row 2 and column 3. What remains is 6 0 8 3. So 6 0 8 3. Then plus 8 capital 3 3. Delete row 3 and column 3. So this part remains 6 0 1 7 determinant. Now we have 1 2 and 3. 3 2 by 2 determinants to compute. But 2 by 2 determinants, we have formula for it. It is the product of the main diagonal entries, 1 times 3 minus 8 times 7. Then plus 5 times 6 times 3 minus 8 times 0. Then plus 8, 6 times 7 minus 1 times 0. Then calculator, we get 161, same number, okay, as the number obtained in example 1. This is an example 2. Now, example 3. Okay, pick rows and columns that have most zeros to expand. Okay, expand. The determinant now is a 4 by 4. 6, 0, 0, 5, 1, 7, 2, negative 5, 2, 0, 0, 0, 8, 3, 1, 8. Yeah, 4 by 4 determinant. Because we can expand a determinant across any row and down any column. To save work, it is wise to pick a row that has most zeros or a column that has most zeros to expand. Solution. Let me see. I can see that the third row has most zeros. So I expand the determinant across the third row. Okay. So across the third row, the third row first entry is A. Third row A31, C31, A32, C32, A33, C33, A34, C34. But now A31 is number 2. A32, 0. This is 0. This is 0. So therefore, 0 times the number is 0. So this is equals to 2 times 31. That's it. Right? We don't need to compute the second, third, and the fourth terms. Right. Then this is what is capital 3.1 by formula -1, 3 plus 1, determinant A31. Yeah, and this is -1 to the 4th, +1. So 2 times A31. Now let me determine capital A31. In the original determinant, delete row 3 and delete column 1. Then capital A31 is 005. 7 to -5. The third row is gone. So the fourth row, 3, 1, 8. And now we have a 3 by 3 determinant to compute. In this 3 by 3 determinant, I can see that first row contains most zeros. So I expand this determinant across the first row. Across the first row. So 2 times, okay, 2 times A11 0 times C11 plus A12 0 times A12 plus A13 5 C13. So therefore, this is the first term 0, second term 0, and then 2 times the number 5, 10 C13. C13. Okay. Let me continue my solution here. Here. Then I get 10 times capital C13. By formula, it is a -1, 1 plus 3. Determinant capital A13. 1 plus 3 is 4. -1 to the 4th, +1. So 10 times A13. Okay. So 10 times, okay, now let me determine capital A13. How? Delete first row. Delete column 3. So the remaining part is capital A13. So I get determinant 7 to 3, 1. Okay, now 2 by 2 determinant, we have a formula. 7 times 1 minus 3 times 2. Then calculator. The number is 10. Number is 10. Done. Because determinant 10 non-zero. So this matrix, this 4 by 4 matrix is invertible. It has inverse. Example 3. Example 4. Example 4. And let matrix A matrix. So I use square brackets. A11, A12, A1n. But the second row is a 0 row. All the entries on the second row, 0. The third row, A31, A32, A33, A3n. The last row, A is square. When we talk about determinant, we assume the matrix is square. AN1, AN2, ANN. Okay, matrix. Now, compare determinant of this matrix. Okay, now solution. Because the second row all are zeros, of course, I expand the determinant across the second row. Determinant is second row, okay, second row. First entry, 0 times C by formula. A21, so C21. Second entry, A22, 0 times C22 plus last entry, A2n, 0 times C2n. But capital C are numbers. 0 times the number is 0, so the answer is 0. Therefore, so A has no inverse because determinant is 0. So this matrix has no inverse. So when a matrix has a 0 row, the matrix has no inverse. Done. Example 4. Example number 5. Example number 5. Example number 5. Let be given the following upper triangular matrix. Yeah, the following matrix is a upper triangular. The size is 5 by 5. 3, -7, 8, 9, 6, 0, 2, 7, 3, 0, 0, 1, 5, 0, 0, 0, 0, 4, -1, 0, 0, 0, 0, -2. The main diagonal line is this line. Yeah, this line is main diagonal line. This matrix below the main diagonal line, all the entries are zeros. Yeah. A matrix with such a structure is called an upper triangular matrix. Upper triangular matrix. Now, find determinant of A. Okay. Yeah. Solution. To compute the determinant, to save work, I expand the determinant down the first column. The first column, okay. First column, A11, number 3, C11. Second entry, A21, 0 times C21 by formula. Third entry, A31, 0 times C31. And then the fourth entry times C41, 0 times C51. Right? So this is equals to just a C11, the first term. Okay. By formula for capital C, it is level 1 plus 1 times determinant A11 by formula. Okay, level 1 to 1 plus 1, positive 1, so 3 times determinant A11. Then what is capital A11? Capital A11. To get capital A11, delete first row. Delete first column. The part remains is capital A11. So determinant 2, level 5, 7, 3, 0, 1, 5, 0, 0, 0, 4, negative 1, 0, 0, 0, negative 2. Yeah. Again, this matrix is an upper triangular matrix. How to compute this determinant? Expand it down the first column again. Yeah, let me write the solution here. Okay. So down the first column times A11, number 2, times capital C11, A21, 0, capital C21, A31, 0, capital C31, and 0 times capitals C41. Okay, so this is a 0 times a number 0, 0, 0. So 2 times 2 times capital C11. Now let me determine capital C11 by formula. It is a negative 1, 1 plus 1 times determinant of capital A11. So this is a 3 times 2. Negative 1 to 2, positive 1, C11. Okay. A11. Okay. Now to determine capital A11, delete first row, delete first column. So this is a capital A11. Let me solution on next page. So again, 3 times 2. Let me see, capital A11, 1, 5, 0. Uh, 0, 4, negative 1. 0, 0, negative 2. Determinant. All right. Is determinant 3 by 3. Again, upper triangular. To compute it, I expand the determinant down the first column. So A11, 1, capital C11, A21, 0 times C21, A31, 0 times C31. So it is equals to 3 times 2 times 1 times C11. By formula, capital C11, negative 1, 1 plus 1 times determinant A11. So this is a 3, 2, 1. Negative 1 to 2 to the second, positive 1, A11. Okay. A11. This is 1. All right, now capital A11. Delete first row, delete first column. Then again, 4, negative 1, 0, negative 2. So for this 2 by 2 determinant, it is 4 times negative 2 main diagonal entries minus anti-diagonal entries 0 times negative 1. So the answer is 3 times 2 times 1 times 4 times negative 2. Go back to the original matrix. 3, 2, 1, 4, negative 2. It turns out that they are the entries on the main diagonal. Yeah. 3, 2, 1, 4, -2. Therefore, for upper triangular matrix, the determinant is equal to the product of the main diagonal entries. Yeah, 3, 2, 1, 4, -2. Yeah, 3, 2, 1, 4, -2. So that. This number calculator. What is the number? Let me see. From my notes. It is -48. Yeah, determinant of the original 5x5 matrix is -48, non-zero number. So the original matrix has inverse. Apart from this example, we see that upper triangular determinant is the product of the main diagonal entries. This is true in general. It is the following figure. Let A be an upper triangular matrix. A11, A12, A13, A1n, then 0, A22, A23, A2n, 0, 0, A33, A3n, and so on. Okay. 0, 0, 0, non-zero, maybe. Okay. Yeah. Upper triangular matrix. Then determinant of this matrix, simple. The product of all the main diagonal entries. It is equals to A11 times A22 times A33. A33 times ANN. Yeah. So upper triangular matrix determinant is simple, just the product of the main diagonal entries. Yeah. This is topic 1 today. Now, second topic. What is second topic? Determinants and row operations. When we reduce a matrix to an epsilon form, there are 3 elementary operations that we use, right? When we reduce a matrix to epsilon form, 3 elementary operations. The first one is we can interchange 2 rows. Second operation is we can multiply some row by some number C, right? And the third operation is some number times some row J plus row I. Some number times row J add to row I. Okay. Yeah. Row I. Yeah. Here, pay attention. Don't put the result C times row J plus row I. Don't put the new row in row J, but put it in row I. It is important to remember. Yeah. A number times some row add to row I. Yeah. Add to row I. Okay. Now, in the second topic, I examine how these three operations affect the value of a determinant. Okay. Topic 2. Topic number 2. First, interchange two rows. First, okay. I have a matrix A11, A12, A1n. Row I is AI1, AI2, AIN. Row J is AJ1, AJ2, AJN. The bottom row is AN1, AN2, ANN. This is a matrix. Now I compute its determinant. So I put vertical line. Vertical lines. Okay. Don't put square brackets. Square brackets means a matrix. Now determinant is a number. Okay. Now let me switch row I and row J. Then I get this determinant. Okay, row J goes here. And then row I here. Hey, the other rows not change. Hey, determinant. It is a number. Okay, number. Okay. Hey, it turns out that there is a relation between this number and this number. The relation is minus. Okay. So when you interchange two rows in a determinant, add a minus sign. Okay. Yeah. Then how about a number times one row? How to change the value of a determinant? Okay. Yeah. Number 2. Say a number times row I. Okay. Yeah. A number times row I. We have a new row. Put the new row. Replace the old row I by the new row I. Okay. Yeah, here. A11, A12, A1n. Row I, AI1, AI2, AIN. The bottom row, NN, determinant. It is a number, okay? Now, I multiply row I by a number, say C. Okay. Then I have a new determinant. How the new determinant related to the old determinant? Yeah, old determinant. AI1, AI2, AIN, AN1, AN2, ANN. Yeah, old determinant. Yeah. Then what is the relation between these two numbers? It turns out that C times, okay, when you this formula says that if C is a common factor of rho I, you can take out C, take out C, take out C, take C out. Okay, C times this determinant. Hey, this is the second elementary rho operation. How this operation affect the value of determinant. The formula is here. Formula is here. Now the operation. The operation. Some number times some rho. Add to rho I. Okay. Add to rho I. Now here. Determinant A11, A12, A1J. Rho I here. AI1, AI2, AIN. Rho J, AJ1, AJ2, AJN, AJN. Here I assume J greater than I, but not necessarily J is greater than I. Here I assume J greater than I. But J can be less than I. Okay. AN1, AN2, ANN. Determinant. Okay, now I perform this operation to this determinant. A number C times rho J add to rho I, then I get this determinant. Okay, number C times rho J add to rho I. So rho I is AI1 plus C, AJ1. The second entry, AI2, C, AJ2, and so on. The last entry is AIN plus C, AJN. Right? Only rho I is change. The other rows not change. So the other rows, say rho J not change. Rho J not change. The bottom row, of course, not change. Yeah. Now determinant. Now the question is, what is the relation between these two determinants? It turns out that they are equal. They are equal. In other words, this operation doesn't change the value of a determinant. Okay. Yeah, this is the relations between determinants and rho operations. Okay. Now, these relations make our computation of the determinant very simple. Why? Because given us a determinant, we can use the rho operations, reduce the determinant into an epsilon form. A matrix in epsilon form must be upper triangular. Therefore, determinant of an epsilon form is the product of the main diagonal entries. Let me show you one example. Very powerful. Okay. Yeah. This way to compute a determinant is much more efficient than to use the cofactor expansion to compute a determinant. Let me show you one example. Yeah, example. Take a look. Example number 1 under the second topic. Find the following determinant. By row operations, okay, to epsilon form. Yeah, I prefer to use this approach, reduce determinant to epsilon form to compute a determinant. I don't like cofactor expansion. Yeah. Okay, determinant 1, 5 by 5. 1, 3. -1, 0. -2. 0, 2, 4, 6, 2, 3, 10, 1, 5, 6, 2, -3. And then 5 by 5, 0, 2, 4, 5, 9. Determinant. Okay, determinant. Okay, now solution. To compute this determinant, step by step, I reduce it to epsilon form by forward elimination. Okay. First, I use this number to eliminate -2 and +1. So 2 times first row add to the third row. This operation doesn't change the value of the determinant. Okay, so again, 1, 3, -1, 0, -2, 0, 2, 4. And then, okay, +2 times row 1 add to row 3. Then the row 3 is 0, 0, 0, 3, 6. This operation doesn't change determinant. Now, to eliminate this number 1, -1 times first row add to this row. Then I get 0, 2, -5, 2, -1. And here is already 0. So so the bottom row is not changed. Okay. Yeah. Determinant. Yeah. Determinant is a number. So this number is equal to this number. Okay. All right. Now I want to transform this matrix into an upper triangular matrix. Okay, now let me switch row 5 and row 3, switch. Okay. When we do switch interchange, don't forget, add a minus sign. Minus. Okay. Determinant 1, 3, -1, 0, 2. Second row. The third row, okay, I switch row 3 and row 5. And then the fourth row, not change. And then 0, 0, 0, 3, 6. Determinant. Okay. This determinant is not in epsilon form yet. Next, I use this number as pivot number to eliminate these two. Yeah, these two numbers. Okay, so -1 times second row add to row 3. This operation doesn't change the value of determinant. And -1 times row 2 add to row 4 also doesn't change the value. So next page. Okay, then I get negative -1, 3, -1, 0, -2, 0, 2. Then zero, 0, 0, 7, 15. 0, 0, -1, 4, 5, 0, 0, 0, 3, 6. 6. Determinant. Yeah. Okay, now the next step, I switch these two rows. Okay, switch these two rows. When you do switch, add a minus sign. Okay, so here, there is a negative. Okay, so -1 times -1. Okay, add a minus sign. Switch. So 0, 0, -1, 4, 5. And then 0, 0, 0, 7, 15. And then 0, 0, 0, number 3, 6. Okay. So negative times negative, positive. Okay. It is still not in upper triangular form, not in epsilon form yet. Okay. Now I can see that row 5, number 3 is a common factor. Number 3 is common, right? So let me move the number 3 outside the determinant. Yeah. Yeah. This operation, yeah, you see, a number common factor, I can move common factor out. So, okay, here, negative, negative, positive, 0, -2, 0, 2, 4, 0, 0, -1. Then 0, 0, 0, 7, 15. Now I move the common factor number 3 out. So 1, 2. So number 3, okay. Number 3 times this number, okay. Okay, now not in epsilon form yet. Next, I switch these two rows. Then again, when I switch, add a minus sign. Zero, 0, -1, 4, 5. Switch, then 0, 0, 0, 1, 2. Then 0, 0, 0, 7, 15. Yeah, determinant. Final step. Use this number as pivot to eliminate 7. -7 times row 4 add to row 5. This operation doesn't change the value, okay, of a determinant. Then again, -3 times 1, 3, -1, 0, -2, 0, 2. Zero, 0, 0, 1, 2, and then 0, 0, 0, 0, 1. Yeah. The final determinant is an upper triangular determinant. So by theorem, this determinant is just the product of the main diagonal entries. So okay. Yeah. Main diagonal entries. Yeah, the product. So this is a 1, 2, -1, 1, 1. So the answer is let me see, -3 times 2, -6 times -1. So 6. So this 5 by 5 determinant. It is 6, 6. Because 6 long 0, so 5 by 5 matrix invertible. This is all for today. Okay, 2 topics, especially the second topic. Use row operations to reduce a determinant to epsilon form. I should say that this approach to compute a determinant is much easier than the approach by using cofactor expansion.